Okay, so first of all, thanks for the invitation. It has been a pleasure to talk to you earlier this morning. I mean, for me, it's morning. And thanks for attending the presentation also. For me, this is going to be very timely because we are revising the paper right now. So comments and suggestions at this stage are really, really mostly welcome. And so this is work with Clarissa Gandur and Juliana Assunção, both from the Climate Policy Initiative, a think tank, and the Catholic University in Rio, so Rio. So this is also timely because if you wonder, the Forest Awakens title, it is a reference to the Star Wars movie, if you wonder. So I was just wishing I could present this yesterday, because yesterday was, May the 4th, and there is this joke about, I don't know, May the 4th. Well, you know the joke. You don't have to laugh. Anyway, so let me start. So the motivation here, I don't think I needed to spend a lot of time motivating the topic. Restoration matters. It's about regeneration, right? So as the forests regrow, they capture and store carbon, and this is actually so this regeneration, this restoration plays a vital role, and it seems to be very cost effective in absorbing carbon and helping, therefore, to mitigate climate change. So it's helping on a global level, but it also has economic impacts at the local level, because it can help protect watersheds and help with agricultural yields and help the livelihood of the locals and so on and so forth. So the United Nations recently has declared this decade to be the decade for ecosystem restoration. So this gives you an idea about the global importance of the topic. And the International Union for Conservation of Nature, so the IUCN, together with the Windrock International, they have estimated that the restoration of about 350 million hectares worldwide by 2030 would have the potential to absorb about 1.7 gigabyte tons of CO2 per year, which is really massive. It's a lot. And that would yield about $170 billion in net annual social benefits. So this gives a sense about the global importance of regeneration of ecosystems. And within that context, Brazil has a unique position because it has the potential for a lot of restoration-based carbon sequestration. It has vast amounts of tropical ecosystems, and in a lot of those, there's a lot of degraded and deforested lands. Yet, in spite of this potential, restoration has not been amongst Brazil's conservation priority over the past 2 decades. It's a little bit different now, to pay attention to that nowadays, but for 20 years almost, for the last 20 years, not so much. So let me show you this picture. Some of you might have seen something like that before, to give you a little bit of a context, and then I'll explain what we do exactly in this paper. So this shows you the amount of deforestation per year between 2000 and 2014. And you see that the amount of deforestation in a given year was very high until 2004, when it reached its peak. So this is annual deforestation, the amount of deforestation happening in a given year. So by 2004, the amount of deforestation was approximately 2.7 million hectares, which is more or less the size of Belgium. So you can think of how big this problem was in terms of deforestation. So think about Belgium completely covered by trees. So we cut all these trees down in a single year, Belgium entirely. So this I believe it gives you a notion about how severe the problem was. So in 2004, Brazil released this action plan with the goal. It was a mix of policies with the goal of reducing deforestation, and the main policy change at the time was the use of satellite, almost real-time satellite-based monitoring system. And after that, deforestation went down substantially to the bottom about 2012, when we deforested just 500,000 hectares, which was the smallest amount in any given year ever since we started recording it. So the reduction in deforestation was about 75%. So huge success. Many policy changes happening during this time period, not just the satellite-based monitoring system. Other things were happening. There's a lot of studies out there trying to understand how much each policy could have contributed to the decline of the deforestation. So nowadays, well, after 2014, it was a little bit stable, and then deforestation has increased again, especially in the last 2-3 years, especially after Bolsonaro took over. So now we are back to the levels we haven't seen since 2008. So it's around, we're around here nowadays, at this level of deforestation per year. So the worst time in the decade, and it's trending upward. All of that to say that a lot of policy changes focused on reducing deforestation. What was not really known at the time is, what about regeneration? And it turns out that the area occupied by secondary vegetation has increased substantially. So secondary vegetation here is areas in which you have vegetation and that were and that experienced clear-cut deforestation before. Right? So you have primary forest, you cut them down, and then you allow the forests to regrow. So by 2004, we had about 10 million hectares of secondary vegetation, and 10 years later, we had about 17 million. So an increase about 70%, which is a massive increase. The 17 million hectares is approximately a quarter of all of the accumulated deforested areas. So if you look at deforested areas, 25% of that is a secondary vegetation. 2/3 of that is pasture. So most of the deforestation goes to cattle ranching. And about 6 to 8% is cropland, mostly soybeans. And the remaining would be things like urban areas or mining, or it's difficult to classify from satellite or covered by cloud, so we don't know. Now, this increase was not just huge, it's also everywhere. So if we put that in a map, so this is the map of the Brazilian Amazon biome. If you know the Brazilian map, you know the country continues over here to the east and down to the south. So it's almost like you have a little cone here, and Rio and São Paulo are into the southeast region. So this region, when you see the green areas, this is called the arc of deforestation. Most of the deforestation happens in these areas here, and so does most of the regeneration. So not just a huge increase in the area occupied by secondary vegetation, also completely spread it out. So what I think is really impressive about this is that regeneration was really invisible. No one knew this was happening. I mean, you couldn't know if you're studying, some places here and there, but no one knew the extent of regeneration at the time. And it was invisible for 2 reasons. First one is that the policy never really targeted regeneration or restoration. So that was not part of the policy at the time. And related, and perhaps more importantly, the satellite-based monitoring system, they were not trying to measure regeneration whatsoever. They basically tried to capture incremental deforestation, and once something's classified as deforested, they just don't look at that place any longer. So regeneration was completely invisible. So we had lots of policies that has been estimated to be key drivers of the deforestation slowdown. Mike Walters have many papers on that. I have worked on this, other really great work by other people showing that. They have really, this monitoring system has increased the cost of engaging in deforestation. So the question we address in this paper is, did the same monitoring and law enforcement strategy aimed at reducing the loss of primary forest unintentionally affected regeneration? So that's the question you want to address in this paper. And the answer is not that trivial, because there are opposing forces happening. So you could think that once you have stricter monitoring happening, the farmers would perceive a higher risk of illegal primary deforestation, which could lead them to switch deforestation from primary forest to secondary forests. Because if they know that the secondary forests were not targeted by the policy, they could just do whatever they wanted there. That would be fine. They wouldn't be caught. So if this is what's really happening, then you have a leakage problem. Reduced deforestation in primary forest and at the cost of increasing deforestation on secondary vegetation. So it's a leakage. We call that displacement in this paper. If this is true, or if this is the dominant factor, the increase in regeneration I showed you before could have been even steeper, had this impact, if this impact were not there. Now, something else could be happening. Maybe the farmers believe, oh, now it's really risky to do any illegal deforestation, maybe in primary or secondary vegetation. So let's just deforest less, maybe we're going to abandon those lands, and we're going to let the expansion of the vegetation to happen. So this, we call this the deterrence effect. So it could be either one. So you're going to try to estimate which force dominates and the magnitude of that. So to give an illustration with a slightly extra piece of information, so this is what we have. So suppose there is law enforcement happening right here. So the authorities realized something's wrong here. Maybe there is a deforestation happening here. If the displacement effect is dominating, we would expect farmers to come here in the forest, the secondary vegetation someplace else. If the deterrence effect dominates, you would see them abandoning the land. So the extra piece of information in this slide that was not in the previous one is that this one gives you a hint about our identification strategy. We are going to look at law enforcement happening in a given place affecting land use decisions in a different place, in a neighborhood place. So that gives you an idea about how you're going to handle this econometrically. Both deterrence and displacement effects, they constitute policy spillovers. So a policy focused on one thing have an impact on something else. And it's also a spatial spillover because it's a policy focused on one place affecting stuff happening in a different place. So that's what you want to do. So next, I'll give you a little bit more of the context. I will talk about the data and how we measure secondary vegetation, which is quite tricky actually. And then I will talk about the empirical strategy and results. I'll spend a lot of time now in the context and the data. The empirical strategy is actually very simple. So once the context and the data is well understood, I don't think we need to spend a lot of time in the econometric strategy. So the context. What I want to tell you is the satellite system that Brazil has. So I'm talking about 3 main satellite systems. There are more, but those are the 3 main systems that we're going to use. The first one is called PRODIS. It was released by the Brazilian, let's say the Brazilian NASA, so the Brazilian Spatial Agency. It was released by in the late 80s. The goal of this system is to identify incremental deforestation. So it is conducted annually, and it has a 30-meter spatial resolution. So it's a very fine resolution. Whenever you see in the news, the amount of deforestation is typically coming from this data. So in year number 1, The brownish area, let's say it's the area that has been deforested in the Amazon. In year number 2, that previously deforested area is going to become part of the so-called deforestation mask, which means that produce will not look at that area anymore, and you try to detect deforestation in other places. So suppose during year number 2, this is the amount of deforestation that happened. So in year 3, this new deforestation here becomes part of deforestation mask, and now we don't know what's happening there. Let's try to detect deforestation in other places, and so on. So this is the first satellite-based system. It's not intended to monitor, sorry, to enforce. It's not meant to monitor deforestation on a high-frequency basis. Now, the deter system does that. It's conducted daily, and then it identifies the clearing hotspots. So the Brazilian NASA identifies the hotspots. They collect that information, they send the information to the Brazilian Protection Agency, IBAMA, and then IBAMA get the information about where the hotspots are, and then they send the inspectors in those places to detect, to check what's going on the ground, and then issue the appropriate fines or the appropriate penalties depending on what's happening there. So if you deforest in a given place, right after you do it, an inspector could just stop by and check what they have been doing. So you can be caught red-handed, if you will. Now, it's conducted daily. It started in 2004, and it was in an experimental mode in 2004 and 5, and it became fully operational in 2006. It became fully operational in 2006, and it has been improved by 2015 in a way that I'll explain in a second. So because it goes over, the satellite goes over the same pixel every day, pretty much, the spatial resolution is not as good. So while PRODES, it has a 30 meters resolution, meaning any deforestation beyond 6 hectares, it's going to be identified. Here, in the deter data, the resolution is 250 meters or 25 hectares. So you can only detect deforestation that's more that is more than 25 hectares. So not as fine. The resolution is not as fine. So in year 2 here, this deforested area in year number 1, that becomes part of the deforestation mask. So deter does not look at that area. It's been deforested. So let's find what's going on in other places. And let's suppose in year 2, the brownish areas are the areas that deter detects as potentially deforested. So INPE, the Brazilian NASA, will issue those hot spot alerts to the Brazilian Protection Agency, and they're going to send inspectors to these places. So you see, it doesn't coincide perfectly with PRODES because you have this difference in the spatial resolution at least. So in year number 3, what happens is deter checks what has been classified as deforested by PRODES and takes that PRODES mask, the deforestation mask, in consideration, and it ignores that again and tries to check what's new, where new deforestation is happening, and so on. So you see, both PRODES and deter completely ignore land use within deforestation mask. So they have no idea what's going on there. Now, you might wonder, so this is what I just said, let me ignore that. So you might wonder, so how could we even measure regeneration to begin with? Because none of these systems, none of them do the job. Then it comes the third system, which is called TerraClass. So TerraClass does just that. It takes the deforestation mask. It doesn't look at other places. It just looks at what's happening within the deforestation mask. and classifies land use there. So for example, it could be that deforestation mask could be composed of pasture land and a little bit of secondary vegetation, and maybe in the following year, there's a little bit more of secondary vegetation, maybe a little bit of crops, maybe something else at expense of pasture land. Now, interestingly, the first year that TerraClass released the information was by 2012. Up to that point, there exists, as far as I can tell, there exists no data set telling you the land uses in the whole Amazon for the different types of land uses inside the deforestation area. So whatever was going on inside the deforestation area was just completely unknown, except for, I mean, you have geographers making studies of here and there, but not at the whole, for the whole Amazon. And not just was that released by 2012, by 2012, TerraClass data corresponding to land use in 2008 was released. That's all we knew. And then after 2012, TerraClass was releasing other data points and finished doing it by 2016. So by 2016, we finally got information about land use inside the deforestation mask for 5 years. So 2004, 10, 4, 8, 10, 12, 14. So in a span of 10 years, we have 5 data points. It's almost every 2 years, except that we don't have 2006. Up to 2016, it's fair to say we were not quite sure what was really happening in terms of land use. So we are going to make use of these three systems. So let me tell you a little bit about the data, so I can go to the empirical strategy. So we're going to use data from deforestation from the produce, the land use in deforested areas from TerraClass, so basically mostly to measure regeneration, and the deter system, we're going to use the alerts for the hotspots from the deter system, the thing that's conducted almost daily. So we have, at the end of the day, we're going to run regressions in which the dependent variable are the amount of secondary vegetation, and the main variable of interest is the enforcement as proxied by the alerts from the deter system, which I'll explain a little bit more in a second. We're going to have a bunch of controls, so we're going to consider weather, satellite visibility, whether it's a protected, if you're looking at a protected territory or not, like conservation units, indigenous reserves, whether the municipality is a priority municipality, and if, in case you don't know, in 2008, Brazil issued, as one of the policies that Brazil issued during that period, they focused monitoring efforts in a blacklist of municipalities. Those are the priority municipalities. And also we consider distance to roads and to centers as a typically those are important variables explaining land use. We split the whole Amazon into, we rasterize the whole Amazon into small cells. We end up with 5 million cells. We don't use all of them. So I'll explain the sample selection in a second, but it's about 5 million cells. And the sample period is from 2004 and 14. We look at this sample period for 2 reasons. One is that this is the time in which monitoring efforts were most intensive. And also it's the time period for which we have the TerraClass data. Now, let me tell you a little bit more about the spatial setup. So suppose this is the Amazon. So as I said, we rasterize the Amazon and split into little cells. The unit of observation here is going to be a cell. It's a 900 meters by 900 meters. So this is going to be 0.81 square kilometer, or 81 hectares, basically. So we will measure things like the shares of those cells that is primary forest, share of the cells that is secondary vegetation. And to do the shares calculation, we split each cell further by these little pixels, 30 meter by 30 meter pixels. So if you have each cell has about 900 pixels on average. So if I have 90 pixels in which land use is classified as secondary vegetation, we will say 10% of the cell is secondary vegetation. As I mentioned before, oh, I should also say one more quick thing here. No, I'm sorry, I'm going to leave that for later. So, sorry, let me move on. I mentioned already that one of the strategies is to see if there is enforcement in a given place affecting regeneration in another place. So we will define neighborhoods. So for a given cell, you have this concentric square ring to be defined as the neighborhood of that cell. So we will look at how the alerts happening in this neighborhood affect the regeneration in a given cell, and we will consider further concentric rings. Right? The wider the rings, they do not include the inner rings. Okay, so the last thing I have to say in terms of data, sorry, I have two more things to say about data before I can show you the econometrics and the results. Measuring secondary vegetation is very tricky. In the Terra class, the areas that were once clear-cut and now contain trees and shrubs, that's the definition of secondary vegetation, and it doesn't contain pasture or commercial reforestation. So the first main difficulty is that regeneration is a very time-consuming process, as you know. So it may take several years that regeneration can show up in the satellite classification. So it's not, we don't want to measure fallow land. So if you see something like satellite classifies that pixel as pasture today, then secondary vegetation tomorrow, and then pasture the day after tomorrow, then the secondary vegetation could be either just a misclassification, it was pasture all along, or it could be secondary vegetation, but it's not really secondary vegetation, it's just fallow land. You just let the trees grow a little bit to recover the land's productivity. So because of that, we not just try, I mean, usually when people try to measure secondary vegetation is about you let the biomass grow, and then you have some threshold saying, oops, if we have that much biomass, that means the forest is regrowing. So all I said means, the implications of what I said is that the very short-term time series variation is very prone to measurement error when it comes to measuring regeneration. That means you're going to have to take a look at a longer time period to detect secondary vegetation. So that's the first problem. I mean, this is a general problem. Every satellite system will have this. Every classification based on satellite imagery will have this. We have to face this difficulty. The second one, I think is specific to our setup, which is the difficulty of distinguishing degraded primary forests from actual secondary vegetation. So let me tell you why I think this is very specific to what we do here. So I have this picture. And by the way, I should also add that Clarissa is responsible for all the nice pictures. So that's why I put them here. I think they look, I really like them. I think they look pretty. So this is what we think is what you wanted to have. The correct classification. So suppose you have year t-1, the pixel is full of trees, Prode is classified that place as forest, Terra class says, oh, it's forest, is out of my scope, so I do nothing. Next year, the same thing, and let's say at year t, there has been deforestation. So Prode comes here and say, oh, deforest, this deforestation increment, but it's still out of scope of Terra class. The following year, that pixel becomes part of the deforestation mask, And now TerraClass decides can classify that land use. And let's say it classifies that as pasture. Let's say the following year, you see a little bit of, trees that start to regrow. And maybe TerraClass already classifies that as secondary vegetation, and maybe it does so in the following year, having more trees growing. So this is all fine. This is the kind of thing you want to capture, that type of forestry growth. That's what you want to measure. So the problem we have here is, think of this alternative scenario. The first year, we have the trees as before. In the next year, the forest has been degraded, which could happen. Maybe because, I don't know, maybe selective logging, maybe logging can be happening. But it still has enough biomass so that Brody sees that as forest. The following year, there's a little bit more of degradation, but maybe it's enough degradation that Brody's decided to say, oh, this is deforestation now. It's not really deforestation, it's degradation, but maybe Brody's identified that as deforestation. At T+1, nothing really happens in terms of what's going on the ground. But since this has been classified as deforestation increment, it's going to be part of the deforestation mask the following year. And now it's time for TerraClass to classify this land use. And so it does and classifies that as secondary vegetation. So nothing happens, and then you have this change in classification. And maybe the following year could happen, for example, that maybe this is deforested the following year and it's converted for pasture, let's say. So the problem here is that forest regeneration, we want to see an increase in the biomass over time as a way to measuring the forest regeneration. And we don't want to confuse secondary vegetation with a degraded forest, because for a degraded forest, we should see the opposite trend. The amount of biomass is going down. So we need to take a look not just at long differences or more closer to the medium to the long run differences, we also need to pay attention to the differences in the trends. So to handle this in a simple way, we decided to have a very conservative solution, which is to just consider areas that meet two criteria. That pixel has to be classified as secondary vegetation for 2 consecutive years in the TerraClass years, so we minimize the possibility that it's a fallow land. And it's also classified as secondary vegetation once classified as secondary vegetation, it never ceases to be classified as secondary vegetation, to capture this idea that we need some type of permanence. So this is going to be our measurement of secondary vegetation, not just the raw data from TerraClass. When doing this, so it's very conservative, you could think of other solutions, so this is what we did. The implication of that is we end up using all the full-time series of the 5 years from TerraClass to classify secondary vegetation. And therefore, when it comes to do the regression, we lose the panel structure. And when it comes to do the regression, we just have a cross-sectional regression to run. So that's an implication of, it's a consequence of this difficulty in measuring secondary vegetation. We're going to skip this. In terms of how we measure the enforcement, so this is what the tool is doing. It's some pixels in a given day. Maybe the following day, this thing is gone. And then the system will issue alerts for these areas. So this is a snapshot of the alerts that happened in July of 2011. So it looks like this. So this is what IBAMA would see and then send the inspectors of those places. Unfortunately, there is no data on which of these hotspots the inspectors went. So we don't know if a hotspot was followed up by inspectors or not. So we're going to use the alerts as our measurement of enforcement, which is highly imperfect, but I think at the moment is the best we have. As you can see from this picture, one alert is covering a large area, perhaps more than one cell. So the way we measure alert intensity will be the total number of alert cells over the sample period as a share of the neighborhood area. So it's a share measurement. We'll look at the 5 rings, 5 neighborhood rings, 5 kilometers, 10 kilometers away, 20, 50, and 100 kilometers away. So pretty large areas. In terms of detection, the deter tends to detect a smaller area than PRODES itself detects, which is not surprising given the spatial resolution. In general, it detects about half of the area that PRODES detect. So there is room for a lot of improvement. And just to mention this, they did improve the system after 2015. So instead of not being able to see what's happening inside, instead of not being able to detect deforestation below 25 hectares, now they can see what's happening all the way up to 3 hectares nowadays. So it's a really an amazing system. So 3 hectares, they can see it nowadays. So by the way, these numbers are much better. This fraction is much better today. So finally, last thing I want to say. So how much am I doing okay on time, Frankie?
Yeah. So you have around 5 minutes to 10 minutes more.
Okay. I think I can handle that. So, so the sample selection here is we're going to look at cells with at least a little bit of a deforestation at the beginning of the period, because forests can only regrow in deforested areas. And we also have a benchmark sample, which is cells containing at least 50% of primary forest in the beginning of the sample period. And that's because while initially when you have bigger deforested areas, you have on one hand more room for regeneration to happen. But on the other hand, if you have more primary forest close by, it's easier for a pixel to end up with more a regeneration, because the forest is a bank seed, you have all the pollinators. So the bigger the primary forest, the easier it is for the forested area to regenerate. So we have this countervailing effect. So we will play a little bit with this 50% threshold. In terms of summary statistics, and then I go to the results, just so you have an idea, our measurement of secondary vegetation in 2004 in our benchmark sample is just, on average, a cell contains 3% of secondary vegetation. And by 2014, in our measurement, it contains about 7%. So a substantial increase in proportional terms. In terms of the alerts, in the closest ring, it's about 18% of the area of that neighborhood received an alert within the sample period. And those fractions are, they go down a little bit for rings that are further away, but they're bigger rings. So it's not so surprising that the share of alerts in those areas go down a little bit. And there is substantial variation, I should also add. Okay, I said a lot about, oh, and by the way, regionally about 80% on average of the cell, about 80% of the cell is covered by primary forest on average in our benchmark sample. And also in the regional data, it says 76, not too different. So I said all of that because all that information constrains what we can do in terms of econometrics strategy, but it ended up being a quite simple strategy. So this is the regression we're running. The dependent variable is the change in the regeneration share of the cell I between 2004 and 14 as a function of the enforcement in the neighborhoods of cell I, and we consider a couple of neighborhoods, plus controls and unobservable factors. So remember, this is not a panel data regression. The parameters of interest are the betas for any given ring or in any given neighborhood. If beta is positive, that means if I have more alerts in a neighborhood area, that means I have more regeneration in that cell. That's the displacement factor or displacement effect. If beta is negative, if I have more enforcement in a given neighborhood of a cell, then there is less regeneration in that cell. That's the displacement or the leakage effect. So you want to see if the beta is positive, it's negative 0, and the magnitude of that thing. In terms of identification, we always care whether the main variables of interest correlate with the observables. And I would say the main argument we have here is that, well, in the crime literature, the main problem they face is that enforcement activities influence illegal behavior, and illegal behavior affects the enforcement. So you have a simultaneity problem in any of the crime literature. Here, it's unfortunate that we don't have that issue because regeneration has been completely invisible to monitoring. So there is no way regeneration can influence enforcement by design. So we don't have the simultaneity problem, and that simplifies our lives substantially. Now, that doesn't mean we don't face potentially omitted variable biases. So we include a bunch of controls. We cannot include self-fixed effects because that's not a panel data regression, but we do include municipality fixed effects. We have a flexible function of latitude and longitude to capture local soil quality or differences in topographies and things like that. We have weather, temperature, rainfall. We take into account the baseline amount of deforested areas and other conservation policies like whether the cell is in a protected area and so on. So these are the results. So I believe I must have, we have like 2 minutes, I guess. I'm gonna skip the robustness analysis and go straight to the main results. So here we're increasing the number of neighborhoods we take into account. The main specification is in the last column. So what we see here is that we find positive effects. So the displacement seems to dominate the leakage, and impact seems to be bigger all the way up to 20 kilometers away, but nothing much is happening after that. Perhaps curiously, the closest ring is not having a significant impact. And we suspect this is coming from some type of heterogeneity that I will explain in a second. In terms of magnitudes, if you increase the alert intensity by 1 standard deviation in this ring and in this ring as well, you effectively increase the change in regeneration by 6% of the sample mean. So in terms of magnitudes, the impacts are, well, it's statistically significant, it's economically relevant, but it's not, the magnitude is not gigantic. And I would not expect this to be gigantic to begin with, because that's an spillover impact. Spillover impacts are not that big, at least not compared to the, typically to the primary impact. So this here shows you the coefficients together with the confidence intervals. So it's a little bit easier to see. I don't think I have the time to talk about this table, which includes progressively more controls, other than qualitatively, most of the numbers are somewhat similar, although they change. What I want to mention is this thing. So this is the benchmark specification. So 50%, the cell has to have at least 50% of primary forest. Now, what happens if you change the cutoff? So this is what I think it's interesting. When you look at the cutoff, which is 10%, that means you're including cells in which you have at least 10% of primary forest. When I have just 10% primary forest, that means most of the cell has been deforested. So this is probably a highly consolidated area. The highly consolidated area, the impact we see in the closest ring happens to be negative. So what we think is happening here is that the leakage matters more for those consolidated areas. And as we move away from the consolidated areas, that leakage stops to being the dominant force. the shape changes a little bit here. We're not exactly sure why the shape is changing. And we don't have a full explanation for what's going on here exactly, but so this is one of the things we want to investigate further. This type of heterogeneity of the impacts. So let me close this by talking about the two simple. So I have one slide for the counterfactual exercises, and then I'm going to conclude. So we did two counterfactual exercises based on those regressions. The first one is, let's say that we improve the monitoring system, and now the tool will detect deforestation everywhere. So let's make it perfect, assuming the probe's deforestation measurement is also perfect. If we do that, then you would have approximately 300,000 more hectares of secondary vegetation happening in the Amazon. We would have had that during that 10 years period, which roughly translates into a 57 million megagrams of biomass or of carbon. But this calculation is very rough, and one of the things we want to do is to improve that calculation substantially, because we have the expansion of secondary vegetation. So that would be like an intensive margin, but also, extensive margin, but also an intensive margin, which is a place that's been secondary vegetation today. We have more carbon in a couple of years. So maybe we can play with both margins and get a better measurement of the amount of carbon sequestration. So we're working on that now. The second counterfactual exercise is, let's see what happens if we have no monitoring system whatsoever. All of those based, look, this is not a structural estimation, so it's all based on those reduced form regressions. If there is no monitoring system compared to the existing system, and the no monitoring system would result in about 100,000 hectares less secondary vegetation. This means that if you go from no monitoring to perfect monitoring, or something closer to perfect monitoring, you would have extra about 400,000 more hectares of secondary vegetation. So to wrap this up, there's always more work to be done. We want to improve the carbon calculation by looking at proper maps of carbon, above ground carbon maps. If you have suggestions about that, we'd be grateful. We can do a better cost benefit analysis. We can compare the benefits coming from the spillover effects vis-a-vis the regional impact of the policy in terms of reducing the loss of primary forest. And you want to disentangle this heterogeneity further. For example, what's happening in public versus private land. What happens if you compare early alerts versus late alerts? We're not distinguishing those right now. And also, our control group can be thought as the places in which you have no alerts. And that can be different depending on whether there's no alert because nothing's happening there versus there is deforestation, but there's no alert. So maybe this could be informative. In terms of policy implications, we hope this is going to help to design the policies. And I just want to finish by reiterating the importance of restoration at scale. As I said, it's one of the United Nations development goals. This is the decade for ecosystem restoration, and Brazil is now paying attention to this. And it plans to restore or reforest about 12 million hectares countrywide, including the Amazon, but also in other places. So hopefully this will help promote and protection of tropical regeneration. And thank you very much. I will stop now.
Thank you, Eduardo, for a very insightful and cool presentation. Yep, so we can take some questions. So we have Danielle. Do you want to ask the first question?
Yep. Can you hear me?
Yeah.
Yep.
Hi, thank you so much. I was wondering whether you address the issue of spatial correlation in all of this, because I mean, there is spatial correlation in the regeneration and the deforestation, and especially in the controls you put in, because if I remember right, you put distance to cities, which sort of creates artificially spatial correlation in your data. Have you played with spatial lag models, some kind of instruments, spatial instruments to address for this, or even just putting spatial correlation as a control, as a starting point?
Yeah, that's a good point. There should be a lot of spatial correlation because those cells are really small to begin with. Right?
There will be, sure.
Yeah, so we're just going back to that. Yeah, here. So you're saying that maybe the land use here correlates with the land use there.
Absolutely. And especially
that's right.
Because the distance increases linearly as your cells move away from each other. So this is by itself some spatial correlation. So
exactly,
that
yes.
needs to be backed up somehow.
Yeah, so if you think in terms of those, let's say, spatial autoregressive models to begin with. So I guess what we're doing here is, so there are three types of correlations to consider. One is if the Y of the other cells affect the Y of your cell. If the axis of the other cells affect your Y, and if the observables of the other cells affect your Y. There could be spatial correlation in either of the Y-axis and epsilon. What we're doing here is effectively allowing the axis, well, at least one X of the other cells to affect your Y, an enforcement in someplace else. We haven't incorporated the spatial correlation in terms of the Y's affecting the other Y's. We could do that, but we checked the spatial correlation in the unobservables, and that would affect mostly the standard errors.
Yes. Do you test for this? Because usually you test from the presence of this in the residuals of this regression, which is just a
yeah, that's right. There is some correlation there. Yeah, you're right. There is correlation in the unobservables, and this is not surprising because there is so much.
No.
Yeah, I mean, they're so close by that all the ecological and geographic variables would have to be very similar to each other. Yeah,
I would be surprised if there wasn't.
You would be surprised. Yeah, that's right. One thing I should say though is so we haven't done everything we could have. That's what I have to say. So we allow for the correlation in observables, but not the correlations among the Y's. Now, one potential justification for the correlation among the Y's is that most, well, that's not a perfect, okay, what I'm about to say, it's not a perfect reason why not to take that into account, but perhaps it helps a little bit. Typically, so typically what's happening is that the farm sizes are typically not that big. Most of the Amazon, they're quite big in some places, but mostly not that big. So that alerts happening in the neighborhood tends to not happen in the same farm that is mostly in the cell of interest. So it's not like I have such a big farm that there is an alert happening in that farm affecting the land use in the same farm. Typically, we can do a better work of checking that because there is more data on farm sizes. Yeah. Because the median size of a farm in the Amazon is about 50 hectares. So it can, one cell can contain 1.5 median-sized farm. So it's basically a story about alerts happening someplace else and affecting decisions in a different place, in a different farm, for the most part.
And I have a follow-up question on this as well. Given this potential issue, have you thought of finding an instrument for your regressor of interest to really pin down the causality mechanism between these two?
Yeah, we would have. I mean, if there is a Y affecting Y, then I guess you would have to have an instrument. So then I don't know. I haven't thought carefully about it, but I guess I can follow a lot of the literature on the autoregressive models to help me out there.
Something or some external thing coming from, you know, precipitation or external sort of potentially exogenous factors to really pin down that the mechanism is X to Y, the relationship. Because otherwise this can be capable, you know.
Well, this can be, but the thing is, this can be sorry, I lost my train of thought for a second. The fact that the alert system cannot possibly respond to the change in regeneration is our main argument for causality. There are other rooms, so in terms of our regression doesn't shed as much light in terms of the mechanisms, why the alert here happens to affect regeneration there. We can speculate on that, but it's difficult to say that this alert system is really correlated with the regeneration, because regeneration is just invisible. So that's the main argument we have. But I mean, we can surely refine the analysis by taking the spatial correlations more seriously into account, beyond what we have done already.
Yeah. Or even lagged versions of your variables could help to understand the dynamics of this as well. I would maybe recommend exploring the lag structure of your data.
Yeah, that would be harder. That would be harder because we used all the time series variation were used to measure secondary vegetation carefully. So that's why we end up with a cross-sectional regression at the end of the day. I mean, I would really like to have, if you ask me, I really would like to have a long panel in which I could take the dynamics very seriously. I think it would be way more informative, but the data constraints have been really severe here. Just 5 data points, yeah. Okay, someone wrote something in the chat. I can't
yeah. So any other questions? I see Brett has written something in the chat, so perhaps I can read some of those questions. So Brett said, so suppose that enforcement in a nearby area leads to more generation, but why did that lead to more regeneration? Because if you think about it, maybe farmers, after they deforest the land, why would they stop having grazing activities after a year or so? Is it because of monitoring, or is it because at least what I was thinking is well, maybe it's slash and burn sort of agriculture, where they burn the forest and use it as fertilizers, and it's no longer like fertile next year. So why would farmers leave the land after a year or so?
Yeah, that's an important question. And when I was talking to Sabrina, she also mentioned, so what do the farmers do when they just stop foresting? Because I mean, they have to make a living somehow. I think what's happening, it's really the story. I think it's mostly about biased beliefs in my estimation. There has been so much effort by the Brazilian government to reduce deforestation overall. I don't think the farmers were aware that the policymakers couldn't really see what was happened in areas that had been deforested already. So they just decided to start reducing deforestation altogether. So that's what I think is happening. If they had that information, or at least if maybe some farmers knew that, and maybe that's why you see a little bit of a negative impact on consolidated areas. I would guess those might be I would have to check where on the negative impacts, where that negative impact is most prevalent. If I were to guess, I would say it's probably in this soybean producing area, because the farmers there are really sophisticated. They really know their business. So maybe they did know that the policymakers were not really checking what's happening in the forested areas. But for others, I would guess they just think of the changes in monitoring as an overall increased risk of doing any illegal activity. So one thing that could be asked in view of that is, well, but maybe they have biased beliefs, but for how long? So maybe they have been biased for so long, and then at some point they realized, oh, they're not doing this. So they're not checking what's happening in deforested areas, so we could just start using. That could happen. I don't think we can investigate that with the panel data that we currently have. But it's a really good question.
Yeah, thank you. We have time for one more question. So I see Sabrina.
Yeah, thanks. I was just wondering whether you could check at the border of the enforcement area, right? So there will be an area that under like for which the government implemented this regulation that you can't deforest the land. And so if you just look at what happens at the border, whether you see the effects on one side and not on the other, because if you're outside of that area, then you shouldn't abandon the land to let it regrow. You should just keep farming it, right? Whereas if you're inside, you may believe that there's monitoring that would basically that the enforcement changes. So if you could look at the border, that may help you.
Yeah, that's a good suggestion. Yeah, maybe you should take a look at that at the border, right? Something more close, something closer to regression to continuity.
Yeah.
Right.
Yeah.
Yeah, that's a good idea. Thank you. Check the border of the enforcement area. Yeah, thanks. I'll check that out. And also, Ben mentioned that if you could just simply ask the farmers. Right? I don't know if anyone did, or at least that we have recorded. Now it's too late to ask, or well, maybe we can ask them and ask their recollections. But I haven't seen that.
This concludes the LEEPout seminar. Thank you, Eduardo, for an amazing talk.